There are all these machines around us, things that just seem to work perfectly, almost like magic. From your thermostat at home to a giant industrial robot, there's often this incredibly simple but powerful concept acting like a hidden brain inside, making countless decisions every second just to keep things running right. Just think about this for a second. You set your car's cruise control to, say, 65 miles per hour. As you start climbing a big hill, the car doesn't slow down, right? It just holds that speed. So how on earth does it know exactly how much gas to give the engine? And how does it know when to ease up? Well, the answer is a beautiful little algorithm that's actually been around for over 100 years. It's called a PID controller, and it is the secret sauce behind so many automated systems. Basically, it's a little feedback loop that's constantly looking at where a system is, comparing it to where it should be, and then calculating the perfect correction to close that gap. It's that hidden brain that keeps everything perfectly in balance. So, here's our game plan. We're going to break down exactly how this amazing thing works. We'll start with our cruise control problem, then we'll look at each of those three letters, P, I, and D, one by one. After that, we'll see how they're balanced in what's called the art of tuning, and we'll wrap up with the incredible history of this one simple idea. Okay, let's dive right in. The whole entire process starts with one super simple calculation, the error. Your desired speed, your set point, is 65 miles per hour. But as you hit that hill, the car's actual speed, its process variable, drops to, let's say, 62. The difference, that 3 miles per hour, that's the error. The PID controller's entire job is to get that error number down to 0. That's it. The first tool in its toolbox is the proportional term, or just P. Now, this is the most intuitive part of the whole thing. It reacts to what's happening right now in the present moment, and it gives an immediate correction that is proportional to how big that error is. In other words, a small error gets a small response. A big error gets a big response. It's that simple. If your speed drops by just 1 mile per hour, the P term gives the engine a little nudge. If your speed suddenly plummets by 10 miles per hour, it's going to slam on the gas. It's simple, it's direct, and it is fast. But P control by itself isn't quite perfect. There's a catch. See, to keep giving the engine that extra power to fight the hill, there has to be an error. So what happens is the controller finds a balance where the car is stable, but maybe it's holding steady at 64 miles per hour, not your target of 65. That little lingering difference is called a steady state error. And this is where the second letter, I for integral, comes in to save the day. The integral term is basically the controller's memory. It looks back at the error that's been building up over time to fix that little shortcoming of the P term. The I term is basically saying, hey, hold on a second, we've been under the speed limit for the last 30 seconds. This isn't just a blip, this is a trend. And as this past error adds up, the integral term applies more and more corrective force. It just keeps pushing until that steady state error is completely gone and you're back at exactly 65 miles per hour. So we've reacted to the present with P, and we've remembered the past with I. The final piece of this puzzle is D for derivative, and this is all about predicting the future. This is the smart, anticipatory part of the controller that stops it from making clumsy mistakes. Imagine you just reached the top of the hill. The error is closing fast. Without that D term, P and I might just keep the power on for a little too long, causing you to overshoot 65 and lurch up to 70. The derivative term sees that the error is changing really fast, and it says, whoa, back off. We're approaching the target quickly. It acts like a brake, applying a damping force to make sure you have a smooth, stable arrival right at your set point, without shooting past it. Now, having these three terms working for you is one thing. But making them work together in harmony, well, that's another story. This is the art of tuning. It's a really delicate balancing act to get the perfect response for whatever system you're working with, whether that's a car, a huge chemical plant, or a tiny little motor in a hard drive. Tuning is really a game of trade-offs, and this table lays it out brilliantly. Let's say you want a faster response time. Okay, you can turn up the proportional gain, that's KP, but be careful, because that's also going to increase your risk of overshooting. The I term is great. It gets rid of that final error, but it can make things a little wobbly. And the D term, it reduces that overshoot, but it can sometimes be a little sensitive to noise. It's all a balance. And you can see that trade-off visually right here. As that proportional gain, KP, goes up from 0.1 to 1, yeah, the system's response gets way faster. But look at those top lines.
The system gets really aggressive, it overshoots the target, and it oscillates a bit before it finally settles down.
Now here's what happens with the integral term. On this graph, t is what's called the integral time, and it's actually the inverse of the integral gain. So a smaller ti actually means a stronger integral action. And as that ti gets smaller, whoa, look out. The system becomes super unstable, with these wild oscillations and a massive overshoot. It's just trying way too hard to correct for all those past errors. And finally, here comes the stabilizing force of the derivative term. As the derivative time, td, is increased, you can just see how it tames the whole system. The overshoot gets dramatically smaller, and all those oscillations are smoothed right out. It's literally like a shock absorber, making sure everything is calm and controlled as it approaches the target. So how did this one really elegant algorithm become such a hidden force that kind of shapes our modern world? Well, this idea isn't new at all. It's actually been evolving for a very, very long time. I mean, the core concepts go back centuries. We're talking centrifugal governors on windmills, early forms of derivative control used to stabilize torpedoes back in 1868. But the real aha moment came in 1922, when a man named Nicholas Minorski, while designing automatic steering for the U.S. Navy, formally laid out the three-term control theory we know today. By the 1930s, it was already an industrial standard. And that industrial adoption, well, it led to this. 97%. That's the percentage of control loops in major U.S. industries that rely on PID controllers. Just let that sink in. This isn't some niche textbook concept. It is the single most dominant control algorithm in the world, running millions and millions of processes right this second, silently and reliably. Which leaves us with a final thought. In an age of just immense, mind-boggling complexity, the PID controller is this incredible testament to the enduring power of simple, elegant ideas. It really makes you wonder, what's the next beautifully simple concept out there that's going to quietly run the world for the next 100 years?